Welcome back. Unit 4 takes the blockchain indoors, private and permissioned chains, the kind that run behind company walls, and the siege of the Byzantine Generals. What makes a chain private? Who uses one and why? A full e-commerce blockchain, state machines, the generals, and we spin up a real private chain with Multichain. Unit 4. Topic 1. Why private blockchain? Meet MegaMart CFO. She's watched 4 units of this course and wants everything blockchain promises, tamper evidence, one shared truth with her suppliers, audits that run themselves. But a public chain is a deal breaker 3 times over. Customer data would be world readable, privacy law forbids it, confirmations are too slow for checkout, and her auditors will not accept anonymous validators. The fix is Unit 1's Types chapter. Grown up. Keep the ledger technology, hashes, blocks, consensus, but move it from the public park into a batch access office. Same machine, controlled door. That's a private blockchain, a company's internal ledger that only vetted members can write to, and only permitted members can read. Characteristic 1. Permissions on both doors. Reading the ledger and writing to it each require explicit, revocable permission from the network's governance. 2. Identity. Every participant is known, vetted, and usually under legal contract. Compare Unit 1's public chains, secured precisely because validators are anonymous strangers. 3. Governance. One organization, or a small consortium, decides who joins, what the rules are, and when to upgrade. Central control is the point, not a flaw. 4. Speed. With 5 known validators instead of 10,000 anonymous ones, consensus takes milliseconds and blocks are final the moment they're written. No forks, no waiting for confirmations. 5. No coin required. Public chains need gas to stop spam from strangers. Here, spam is handled the corporate way. You know exactly who did it, and you revoke their badge. 6. Privacy by access control, and no proof of work electricity bill. Permissioned algorithms, coming later this unit, are practically free to run. The decision worked. A hospital group sharing patient records. Public chain fails privacy. A plain database is private and fast, but the admin can quietly edit history, and rival hospitals won't trust one owner's server. The private chain is the only column with 4 ticks. And the honest footnote worth an exam mark. If a single party controls everything and nobody outside needs proof, a plain database is cheaper, faster, and simpler. Private blockchains earn their keep only when several semi-trusting parties need one tamper-evident record. Unit 4. Topic 2. Private blockchains. Examples and open source. Example 1. Hyperledger Fabric, the enterprise workhorse, stewarded by the Linux Foundation. Its signature move, channels. Private lanes where only chosen members see the data. Its contracts are called chain code, written in everyday languages like Go and Java. Example 2. R3 Corda, designed by a consortium of banks. Its radical idea: there is no global ledger everyone holds. Each transaction travels only to the parties involved. Privacy by architecture, for markets where even the existence of a deal is secret. Example 3. Quorum. Born at JP Morgan, Ethereum, taken private. Everything from Units 2 and 3, Solidity, the EVM, works unchanged, with private transactions and a membership gate bolted on. Example 4. Multichain, Bitcoin's battle-tested code, forked and fitted with a permissioned system and data streams. Hold this name. At the end of this unit we spin one up, live, in 6 commands. A puzzle. Every platform we just met is open source. Why would companies building private chains publish the code? Think bank vaults. Banks don't invent secret vault designs. They buy vaults whose blueprints the whole industry has attacked for decades. Open code can be audited by every consortium member, has been battle-tested by thousands of eyes, can't hold you hostage to one vendor, and is maintained by an industry instead of one team. The exam line. Private describes the network's membership, never the code's visibility. Unit 4. Topic 3. The e-commerce example. An online order touches 5 companies: the marketplace, the seller, the warehouse, the delivery partner, the payment processor. Today each keeps its own database, 5 private versions of the same order. When the databases disagree, I shipped it never arrived, nobody can prove anything. Reconciliation takes weeks of emails, and the customer waits. Sound familiar? It's the Village Notebook problem from Unit 1, wearing a business suit. ShopChain. The 5 companies form a consortium and run one private blockchain. Every event in an order's life is assigned timestamped entry that all 5 hold identically. Disputes don't take weeks, they take one query. Every private blockchain defines an instruction set. The commands members may write to the ledger. Here is ShopChain's, and we'll walk order number 1042 through all of it. Command 1. Create order. Only the marketplace may issue it. Order 1042 is born. Buyer, items, amount, timestamp, signed with the marketplace as key. Unit 1 signatures, on the clock. Verify payment. The payment processor, and only the payment processor, attests the money is real. Its badge allows this one command. It couldn't create an order if it tried. Update inventory. The seller decrements stock. Note every command names its actor. The permission system from topic 1, now enforcing WHO can say what. Pack order. The warehouse signs that the parcel physically exists and left shelf WH3. Ship order. The delivery partner takes custody and commits a tracking number. Custody handoffs are now signatures, not promises. Confirm delivery. The buyer's doorstep signature is hashed into the ledger. The order's story is complete. 2 remaining commands complete the set. Refund, which needs multi-party approval. Next topic, and query order. When the buyer claims the parcel never shipped, query order replays the trail. Packed at warehouse 3. Custody taken. Tracking 9981. Doorstep signed. Signed evidence. Seconds. Case closed. Unit 4. Topic 4. Smart contracts in a private environment. Units 2 and 3 taught smart contracts in the public wild. Indoors, the idea survives. Code enforcing rules, but the economics and the trust model change. 4 differences to master. Difference 1. No gas. Gas existed to make spam expensive for strangers. In a members-only network there are no strangers. Abuse is handled by governance, not fees. Contracts run free. Difference 2. The thing that does not change. Determinism. Every members node replays every contract, and all must land on identical state. Why that's non-negotiable becomes crystal clear in the next topic. Difference 3. Language freedom. Hyperledger Fabric calls its contracts chain code and lets you write them in Go, Java or JavaScript. Quorum keeps Solidity and the EVM. Everything you learned in Units 2 and 3 transfers straight across. Difference 4. Endorsement policies replace open consensus. A contract's result becomes valid when the required members sign it. Named parties, not anonymous minors. Policy is written per contract. The refund contract carries the policy any 2 of 3. The marketplace endorses. The customer proved damage. The payment processor endorses. The money trail checks out. The seller sulks and abstains. 2 of 3. The policy is satisfied. The refund executes and lands on the ledger. No single member could force it or block it. That's public chain trustlessness. Rebuilt indoors with named parties. And one more difference. With unanimous governance, private contracts can be upgraded. Powerful, and a responsibility public chains never grant. Unit 4. Topic 5. State machine. Analogy. Every board game is a state machine. The board is the state. The legal moves are transitions, and the rules make illegal moves impossible. Chess has no move that turns a pawn into a helicopter. 3 words define the whole idea. State, every current value. Transitions, the commands allowed to change them. Determinism, the same commands in the same order always produce the same final state. Now the reveal this unit has been building to. A blockchain is a replicated state machine. The chain of blocks is nothing more than an agreed order of commands. Every node replays them from the genesis block. and because transitions are deterministic, every node must arrive at the identical state. This is why contracts can't roll dice or read the clock. One node's dice would differ from another's, replicas would diverge, and shared truth would shatter. Determinism isn't a style rule, it's what makes replication possible. Here's the whole e-commerce example redrawn as one diagram, the states, and the only commands that move between them. Unit 2's Little Pizza Enum was this exact idea in miniature. And the machine's real power is what cannot happen. No command jumps an order from created straight to delivered without payment, packing and custody in between. Fraud isn't forbidden by policy, it's unrepresentable by construction. That's what code as law actually means. Unit 4, Topic 6. Algorithms of permissioned blockchains. Why do private chains get their own consensus algorithms? Because the threat model shrinks. No anonymous strangers means no need for proof of works electricity or proof of stakes collateral, but two dangers remain. Danger 1. The crash fault. A member's server just dies. Power cut. Full disk. A bug. It isn't malicious. It's simply gone. Mid-conversation. Danger 2. The Byzantine fault. Named for the generals you'll meet next. Topic. A node that lies. Hacked. Buggy. Or corrupt. It tells one peer yes and another no. Far rarer indoors, but a hacked consortium member is exactly this. RAFT, the crash fault workhorse. One node is elected leader. It orders all commands and streams them to the followers. Simple, fast. Hyperledger Fabric uses it to order transactions. When the leader crashes, followers notice the silence, hold an election, majority vote, and crown a new leader in milliseconds. RAFT survives crashes beautifully, but if a node lies, RAFT is defenseless. It trusts every message. The family portrait. RAFT, crash tolerant, needs a bare majority. 3 nodes survive one crash. PBFT and its Ethereum family cousin IBFT tolerate liars, but need 3F+1. 4 nodes to survive one traitor. Proof of authority and proof of elapsed time you know from Unit 1. Memorize the pair of formulas. Crashes need 2F+1. Lies need 3F+1. Why liars cost so much more? That's the siege we've owed you since Unit 1. Unit 4. Topic 7. The Byzantine Generals. 4 armies surround a fortified city. If all 4 attack at dawn, the city falls. If even one hesitates, the attackers are slaughtered piecemeal. Total coordination or total disaster, nothing in between. The generals coordinate the only way ancient armies could. Messengers riding between camps. Messengers get captured. Messages arrive late, or never. And one more problem. General 3 is a traitor. He tells the generals on his east flank attack and the west flank retreat, hoping to split the loyal armies and doom them. This is the Byzantine fault. Not silence, but confident, targeted lies. Why not just vote? Because each general only sees the messages sent to him. The traitor feeds different lies to different generals, so their tallies disagree, and each loyal general, acting on his own honest count, does something different. Simple majority voting shatters exactly when you need it. The 1982 breakthrough. Lamport, Shostak and Peace. The generals must exchange not just orders, but reports of what they heard, in rounds. Cross-checking reports exposes whoever's story keeps changing, and the arithmetic demands numbers. To survive F-traders you need 3F+1 generals. 4 generals can beat 1 traitor, 3 cannot. Now swap generals for servers. PBFT, Castro and Liskov, 1999. Turned the siege mathematics into a protocol fast enough for real systems. 4 replicas. 1 may be a traitor. 3 phases. Watch closely. Phase 1. Prepare. The leader assigns the request a sequence number. This is command number 42, and broadcasts it. The leader is the general who proposes the battle plan. Phase 2. Prepare. The cross-check that defeats traitors. Every replica tells every other replica I heard. Command 42. Each node now compares reports. When 2 F-matching reports arrive, 2, with 1 possible traitor, The node knows the honest majority heard the same plan. Phase 3. Commit. Each node announces I'm prepared. On 2F+1 commit messages, 3 of 4, the command executes and the reply goes to the client. Done. And note what did not happen. No forks. No waiting 6 blocks. PBFT finality is instant. Now let replica 3 turn traitor and send conflicting prepare messages. It fails instantly. R1 and R2 cross-check with each other and the leader. The traitor's story is outnumbered 2 to 1 wherever it lands. Honest nodes simply never see 2F matching reports for the lie. And if the leader lies, the replicas time out and elect a new one. A view change. The scorecard. Byzantine proof up to a third of members. Instant finality. But everyone messages everyone, chatter grows with the square of the node count. Perfect for 20 known members. Impossible for 10,000 strangers. That's why PBFT rules the boardroom. And proof of work rules the park. Unit 1's 20-second preview. Fully earned. Unit 4. Topic 8. Multichain. Multichain. Take Bitcoin's battle-hardened code base, Unit 1's original machine, fork it, and bolt on the 2 things a company needs: a permission layer, and streams for storing data, a private chain in minutes, no consensus engineering required. 3 concepts: granular permissions, connect, send, receive, mine, admin, granted per address, native assets, so issuing a token takes 1 command instead of a Solidity contract. And streams, append-only key-value logs, tailor-made for audit trails like ShopChains. Command 1. Create the chain. 1 line generates the genesis parameters for a brand new private blockchain called ShopChain. Command 2. Start the node. It mines the genesis block, Unit 1's block 0, now yours, and begins listening for members. Command 3. Badge a member. The warehouse's address may now connect and transact, but not mine or administer. The characteristics from topic 1, as an actual command. Command 4. Create the orders stream. The append-only log our e-commerce commands will live in. True means any permitted member may write. Command 5. Publish. Order 1042 status lands in the stream, wrapped in a real transaction, signed and hashed into a block. And Command 6. Read it back. The entry, its data, and its confirmations. A private blockchain, from nothing to a running, permissioned audit log, in 6 commands. That's Multichain's whole pitch. You've now seen the private chain story end to end. Why companies want one, who provides them, how contracts and consensus change indoors, and 1 running live, 1 unit remains. Blockchain meets the real world. Unit 4. Complete. You know what makes a blockchain private, when it beats both a public chain and a plain database. And who builds them? You walked an e-commerce chain command by command, saw contracts and consensus reshaped for known members, learned why a blockchain is a replicated state machine, finally solved the Byzantine Generals with PBFT, and launched a real private chain with Multichain. Next, the finale. Unit 5 sends blockchain into the real world: banking, education, energy, healthcare, real estate, supply chains and the Internet of Things, and then tells you the honest truth about its limits. See you there.